Next, let's look at our simple zero, which can be represented by 1 plus j omega divided by z1, where z1 is the location of our zero. So notice now we don't have either purely real or purely imaginary, but we have a sort of combination. So if we want to compare this on our complex plane to what we've been seeing before, so now we have, here's our imaginary, here's our real axis. So now we're going to have some real part, in this case 1, and some imaginary part, omega over z1. So let's say we have omega over z1 and 1. So this is for so positive values, we'd have our point be somewhere like here. And so of course we're interested in this magnitude, this difference from the distance from the origin, as well as this phase angle theta here. So if we want to find our magnitude, we can do that from our equation c equals the square root of a squared plus b squared. And our phase is going to be the inverse tangent of b over a. And then it's just a matter of substituting in. For our a, we see in this case is 1, and our b is the omega over z1. So let's look first closer at our magnitude. Okay, so for our magnitude, again, we want the gain in decibel is what we're going to want to plot. So we say that's going to be 20 log base 10 of, and now we want the magnitude of 1 plus j times omega over z1. Okay, and so we're just going to use that sort of Pythagorean theorem to get, so remember we have sort of two sides of our triangles here, so we're going to use Pythagorean theorem to get that magnitude c. So we can say this gain in decibels is 20 log of the square root of 1 squared plus the quantity of omega over z1 squared. So we get something that looks like that. So this is a little bit more difficult to visualize than the previous cases we've considered. So what we can do is we can sort of consider extreme cases, and then we're going to make sort of an approximation. So as our first extreme case, let's consider if we have omega equals 0, or let's consider as omega goes to 0, rather. So our frequency is going towards 0. So what's going to happen from this equation? Well, that second term under the radical will go away. We're going to be left with square root of 1 squared, which is just 1. So we'll have that our gain in decibels is equal to 20 log base 10 of 1, which is of course just 0. The other extreme is we can say, well, what happens as our frequency is going to infinity, as it gets really large? Well, in this case, that omega term is going to dominate, and it's basically going to sort of overshadow the 1 squared out front and the z in the denominator as it gets large enough. So we'll be left with that this gain in decibels is just equal to 20 times the log base 10 of omega. And so this is what we saw with our 0 at the origin in the previous video. And so we know that this leads to having a slope of 20 dB per decade. Slope of 20 dB per decade. Okay, so we kind of know how it behaves at the two extremes. So what we're going to do is we're going to use something called a piecewise linear model. And so we're going to make two approximations, and we're going to use linear approximations in those two regions and then join them at a point. So piecewise linear model. And so of course one of our sort of pieces is from this first point, so we're going to have 0 up to a certain point. After a certain point, we're going to have a slope of 20 dB per decade. So the question then becomes, what is our connecting point? So our connecting point between those two linear regions And remember, these are linear approximations, and we'll come back to that in a little bit. So linear approximation. And so what we're going to do is we're going to assign that a value, and we're going to say, let's make that sort of that transition point when omega is equal to the 0 value. And so we have several different names for this sort of transition point. You'll see this called the corner frequency. You'll also see this called the break frequency. And maybe the most common one that you'll see is the 3 dB frequency. So all of these, of course, mean the same thing. Okay, so let's try to put this in terms of our plot up here. So what we're saying is that we have some 0, Z1, and then just to kind of give us a scale, this is still a log scale, so maybe here we have 0.1 times the 0, and over here we have 10 times the 0. So we have something like that. So we're saying that let's make the 0 our corner frequency. So if that's our corner frequency, it's joining the two linear regions. So it's going to have to be at 0 because remember, for lower frequencies, we just have a gain of 0. So our gain in decibels is 0 for lower frequencies. So we have something like this. So now the second piece is saying that we have a slope of 20 dB per decade for high frequencies. And so we're saying if we're above omega equals Z1, we're in that 20 dB per decade slope region. So if I come over here and I say, let's make this 20, so then if we increase 1 decade from Z1, we're going to be at 10 times Z1. And we have this point here, so we can then draw our line, and of course that's going to continue like that. And so this has a slope of 20 dB per decade. And so that would be what the gain of our Bode plot looks like. So again, the blue here is our Bode plot. And so the reason I specify that, let me clean that up a little bit. So this is our Bode plot. So the reason I specify that is because remember back when we first started talking about Bode plots, we said Bode plots are a good approximation, but they're not as good as simulation. So if we were to actually do a simulation and we were to get a curve for a simple 0, the gain of the magnitude would look something like this. So we'd see it agrees pretty well for areas of low frequency and for areas of high frequency, but we have the most disagreement at this point, our corner frequency Z1. And so if we actually went and we looked at the difference between here, so let me just label this as sort of the exact or the actual values. And so we could get better at representing that with something like a simulation. So if we were to come in here though and we were to look at the distance between these 2 points, we would find that it's approximately 3 decibels. So that's why we call that omega Z1 the 3 dB frequency. But again, for first approximations, this blue curve representing our Bode plot is going to give us a good idea of what's going on with the system. Okay, so now let's look at our phase. So we've sort of looked at half of the information with our magnitude, so now we want to consider our phase. So our phase from our equation that we wrote up here earlier with our tangent, so our phase is going to be the inverse tangent of, in the numerator we have b, which is omega over z1, and in the denominator we just have 1. So of course we can simplify that and just say that's inverse tangent of omega divided by z1. Okay, so again, this maybe isn't super obvious to visualize, so we want to sort of pick a few points and see if we can't make an approximation. So let's consider what happens if we have omega equals 0. Well, if we have omega equals 0, that's inverse tangent of 0, which gives us a phase angle of 0 degrees. Other points of interest that are going to work out well are going to be if our omega equals z1, so that makes the argument of the inverse tangent 1. Inverse tangent of 1 is going to give us 45 degrees. And then we can say, well, let's just let omega get really large. And so what that means is that our inverse tangent of that is going to be equal to 90 degrees. And so if it's not as obvious, just thinking about our inverse tangent function, we can come back to thinking about in our complex plane, and we're talking about as this omega value here, as this omega value is increasing, essentially this point looks like it's getting closer and closer to this imaginary axis. So for omega of 0, we're on the real axis, and then we're sort of moving towards our imaginary axis. Okay, so we get something that looks like that. So we've got a few points. So what we want to do is we can do a straight line approximation, so kind of similar to what we did before for our magnitude. So straight line approximation. And so what we're going to do is, let's say we know sort of the middle point is for our omega equals z1, we know that our phase angle should be 45 degrees. So then let's go a lot smaller and a lot bigger. So for a lot smaller, let's say we go 10 times smaller. So we're saying for omega less than or equal to z1 over 10, so a tenth of that 0 value. We're going to say now we're small enough so that we can approximate our phi as 0. And similarly here, if we say we go a lot bigger, so let's say for omega is greater than or equal to 10 times z0, we're going to say our phi is approximately 90 degrees. And so we'll go up there and plot this in our plot in a little bit, but just looking at these points here, we can see we're going to have a slope that's equal to 45 degrees per decade. Okay, so let's come up here to our frequency plot and let's put in some of these key points here. So we've got 0.1 z1, z1, and 10 times z1. So also of interest are going to be our 45 degrees and our 90 degrees. So let's just kind of make a little grid here so that hopefully this turns out a little better. So what we had said is that for 0.1 z and less, we just have 0 phase angle. At 45 degree, or sorry, at omega equals z1, we're saying we have 45 degrees, and at 10 z1, we're saying we have a 90 degrees phase angle. And above that, it just remains at the 90 degrees. So if we do sort of a linear approximation, so up here we have just 90 degrees, and then we have something that looks like that. So of course that should be going through all of those points there. So this blue curve, again, would be our Bode plot. So again, keep in mind our Bode plots are an approximation. If we were to look at what the curve actually looked like, we'd see it does something like this. So we go a little bit under, and then a little bit over here, and then more or less agrees there. So this is our actual curve. And so we can get more close to that using some type of simulation. But again, in most cases, our Bode plot is going to give us a good first approximation that's going to be sufficient for most cases.